Good afternoon everyone, welcome to the channel. Today I want to talk about convolutional neural networks, which are supervised learning frameworks in deep learning, and they can be used for image classification very effectively. So let's get started. First I want to give a header. Okay, so import the required libraries. We need torch, import torch vision, import datasets, transforms, import numpy, and matplotlib. So these are our required libraries. Now I have to define the device. Let's check the PyTorch version. Sorry, f string. Coda f torch is available, else CPU print device is total number torch coda device count. Sorry, bracket issue. Okay, so our PyTorch version is on 12.0. NVIDIA RTX A5000 is GPU. Coda available. Total number of GPUs is 1 at this time. Load USPS dataset. train dataset, datasets.USPS. So root in current working directory within this folder, USPS dataset will be downloaded. Train true, download true, transforms dot root and so. Also do the same for test. So in that case, train will be false. I think everything else is okay. Okay, so our dataset has been downloaded within this folder in the current working directory. So let's check few things. Len train dataset, also the test. 7291 train samples, 2007 test samples. Train dataset dot data shape. Same for the test. So you got the number of samples and 16 by 16 images of digits. So let's visualize a few of them. Visualize few images from the training samples. So let's plt dot figure fix size 15:5 for image on in range 15. Figure on dot add subplot on 15 1 rows 15 columns. Also mention the position image on +1. plt to RAM show train data set image on CMap gray. Also let's see the labels as well. Title, train dataset dot targets image 1, font size will be 20. So plt dot access off. So these are the first 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, first 16. Sorry. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. First 15 images from the train samples. Let's check the same for test. So let's change few things. Here 2 test. This will be 2. and these are the first 15 images from the test samples. So 96366 0006962240 654736 31017011 7. Now it's time to define the data loaders, which will convert our dataset into an iterable. Train data loader, train dataset, batch size 32, shuffle true for train. Same for the test. This is a test. This will be false for shuffle double F. Okay. Okay. Print lane. Train data loader. Test. So this is the length of each data loader. 228 for train case, 63 for test case. Okay, now it's time to define the network architecture. So we have to create a CNN class. NN.module contains all the basic building blocks for creating neural networks in PyTorch. So constructor, super, just like the usual stuff. Now there are two parts in convolutional neural networks. One is feature extraction part, and the second one is classification part. So at first start with the feature extraction part. So we will use convolutional layers, 2D convolution for image, channels 1 because these are grayscale images. Our channels, let's say 64, kernel size 4, straight to padding 1. Also want to add batch normalization layers. This will match the output of the previous layer. Then max pool 2D, kernel size 2, straight 1. Let's apply non-linear activation, reloop, true. Let's copy, repeat. So this will be 2. Okay. Now the input and change 64. This will be 128, and this will match the previous output. Okay. So this is our feature extraction by sliding kernels over the input image. The second part is classification. This is a fully connected network. We will contain this using the linear layers. In features 512, out features 256. Let's use dropout. %50. Relo true. Okay, let's copy this. Okay, so this will be 2. So in features will be 256, out features will be 128, and let's add the final layer. 128 and 10 for 10 classes. Now we have to write the forward method. Pass it to the feature extraction part. After that we have to flatten the input before providing it to linear part. So this will keep the path size fixed and multiply everything else like channels height width. Then we'll pass this one to classification block. Finally return X. Now let's visualize. Visualize the model architecture. So create an instance, CNN, send it to GPU. Summary, model input size. So this is our batch size on channel for grayscale images, and this is the height and width of the USPS images. Sorry, made a mistake. This will be 3. Now finally it's okay. So you can see how the tensor shape is changing. So this part is the feature extraction part. After that we flatten this, and then this is how it is changed, and finally get this is 10 for 10 classes. So the reason for writing 512 here is that if we check the final output of feature extraction, we'll keep the batch size. This is batch size, this is fixed, this will be fixed, and this -1 will multiply other three. So for example, let's see, if I multiply, I get 512. This is what it is doing, multiplying these three and keeping it fixed, then providing it to our classification block. Okay, now define the train batch. Data labels, model criterion, optimizer. For train batch, we have to set the model into train mode, send data to GPU. Since this is supervised learning task, we have to send the labels as well to GPU. Output, after passing the data to model, we get the output. Then we have to calculate the loss. Three common steps: optimizer zero cut, loss backward, optimizer step. Then return the loss. We have to define the test batch as well. So with torch dot inference mode, test batch, data labels, model criterion. We do not need optimizer for the test batch. We have to set it into eval mode, send data to GPU, data to device, labels to GPU, labels to device, model data, loss criterion, output labels. Return loss. We have to define the accuracy function with torch dot inference mode, accuracy data labels model. Set the model into eval mode, labels to device, output model data, output dot max -1. This will give two outputs. So this is basically predicted values of the predicted values of the predicted class, and this is the index of the predicted class. We do not need the values, we only on the index. Okay, then correct pred labels. If pred labels equal to labels this, then this will be considered correct. Correct CPU from tensor will convert all the labels to numpy, and also after converting to numpy we'll convert it into a list. Okay, now set of model. Our model is CNN. Criterion and optimizer. Criterion is also known as loss function. Optimizer. So let's create a model instance. Send it to GPU. Criterion nn dot cross entropy loss for image classification or multi-class classification. Optim dot atom CNN parameters. So CNN parameters. Learning rate, let's say 0.001. Now it's time to train the model. So np dot at first set the seed. So n epochs 5. We will train the model for 5 epochs. Train loss, create to list, test loss. Train accuracy, test accuracy. For epoch in range n epochs. Train losses, test losses. Train accuracies, test accuracies. For data labels in train data loader, train batch loss. We have to call the train batch function. Provide data labels CNN, criterion and optimizer. Train losses. Append the per batch loss into a list. Train batch loss item. correct. Call the accuracy function, provide data, labels, CNN. Train accuracies. Extend train per epoch loss train losses dot train per accuracy train accuracies. So we have to do the same for the test case as well. We have to change so many things. This will be test batch, data level CNN. We do not need optimizer in this case. This will be test batch loss, test losses, test batch correct, test accuracies, test batch correct, test losses, test per epoch accuracy, test accuracies. I hope you have written everything correctly. Train accuracy append. Same for the test. Finally print epoch plus 1 in epochs. Let's copy. This will be test loss. .4f, then train accuracy, .4f, so finally test accuracy. I hope nothing is wrong. accuracy. Okay, so our training is finished. Dataset is very small, so it didn't take much time. Now let's plot model. And accuracy figure. Fixed size 16:4. Onto one. ALT.plot train loss. Red label will be train loss. Test loss. Test loss. PLT.title. Loss curve. Font size 25. We have to add X level and Y level as well. X level, this will be Y level. So X level will be number of epochs. Losses. PLT.x takes Y takes font size 20. PLT.legend font size 20. We have to, this is for loss, we have to repeat this for accuracy as well. So in this case it will be 2. Losses will be accuracy. Okay, so accuracy test accuracy instead of loss curve it will be accuracy curve. Number of epochs, this will be accuracies. Accuracies, let's see. Okay, so red on is the train loss. It decreases a little bit further, so 0.23, and this is slightly higher, 0.30. And this is the accuracy. Train accuracy after 5 epoch 97%. Test accuracy, okay, it doesn't look correct. Oh, sorry. Test, I guess. So I made a mistake. Problem with copy paste. Train accuracy, test accuracy. I think other things are okay. These look different. So let's train the model again. Okay, now it makes more sense. So 0.23, 2259, 0.30, 0.9752, 0.94. So this is slightly higher, slightly lower. Okay, so these are the results after 5 epochs. 13 model prediction, samples, labels for A in range 15, samples, append, output, CNN, pull our model or retrieve our model from GPU, samples, and squeeze. We have to add an extra dimension for making it web size, channels, height and width format. Red labels. Output.max. Same as accuracy. This will give us the predicted value of the class and index of the class. We only need the index. And then we will append them to the labels list. These will be tensors. Initially these will be tensors, so we have to convert them to integer. Figure axis alt.subplot on row 15 columns, fig size 18.5. For I in range 15, axi dot imshow, sample size 0, squeeze, cmap gray, axi title, samples I1, font size 20, set color magenta. These are actual labels. Now I want to mention a condition in samples labels I, then axi dot xlabel labels I, font size 20, set color blue. Correctly predicted labels. If this is not the case, then we'll change the color to red. Wrongly predicted labels. AXI set X ticks, empty the x-axis, empty the y-axis. I hope it's okay. What happens? Oh, sorry, it's not CC, CNN. More problem. Subplot, sorry, not subplot. Okay. Font size. Something is wrong in this line. Sorry, it's not title, it's set title. Okay, really? Okay, I have made the same mistake everywhere. Set not. This axis works a little bit differently than PLT. What is happening? Sorry, this is not 0, this is 1. My goodness, disaster. Okay, so let's look at this model prediction. So we have set the actual levels to what to say, magenta. So these are actual levels 9636600069622240, and if the actual levels match the predicted levels, so we get the predicted levels from here and we append it to a list. So then we correctly predicted levels, we set the color to blue, but if it is not correct, then it will change to red. So for these first 15 samples we haven't got any red, so I guess all of them are correctly predicted, which is expected because you can see the accuracy is quite high. Okay, this is how we can build CNN using PyTorch, and I have shown this example using USPS dataset, which look like this, very low resolution, handwritten digits. So in the next video I will build an artificial neural network which doesn't use the convolutional layers that we have shown here. In that case we'll use linear layers. Okay, so thanks for watching this video. Goodbye.